Welcome, and thank you for stopping by my AIChE talk. My name's Andrew Rosen, and today I'll be talking about how we can tune the reactivity of metal-triazolate frameworks, a subclass of metal organic frameworks, for the catalytic oxidation of strong CH bonds. So I'll first start out by explaining why metal organic frameworks, or MOFs, are an interesting class of materials to study for catalytic reactions. MOFs are composed of inorganic clusters, or nodes, connected to one another by organic linking units to yield a periodic framework material. Most MOFs are highly porous and crystalline, and typically have predictable, tunable structures that can be tailored for a given application of interest. For instance, you can imagine functionalizing the linker, or swapping out the metal at the node, or considering new building blocks altogether to make one of the several thousands of MOFs that have already been synthesized to date. In this way, it becomes possible to impart specific chemical and physical functionality that's tuned for a given catalytic reaction. This structural tunability is also extremely useful because you can use this as a platform to identify structure property relationships in catalysis by exploring how different changes to the metal organic framework structure influence the overall catalytic reactivity. And the last point I want to make here is that MOFs can be thought of as hosting well-defined, spatially isolated metal sites located at the inorganic nodes. This can be extremely beneficial because we then have a very good understanding about what the potential active site structures would look like. This is in pretty clear contrast with most of your conventional catalytic materials, where there's either a wide distribution of potential active sites or it's just very difficult to identify what the active sites are. Naturally, the well-defined nature of MOFs and their metal sites can be helpful in interpreting the results of experiments, but it's also really helpful for the purposes of carrying out computational studies too, since you know the identity and location of all the atoms in your catalytic candidate. In today's talk, I'll be discussing how we can use density functional theory calculations to identify promising MOFs for the catalytic oxidation of strong CH bonds. In particular, I'll be focusing on the conversion of methane, given its societal relevance. The conversion of methane to methanol is one of these so-called holy grail reactions. Conventionally, what we can do in industry is convert methane, typically found in natural gas, to synthesis gas, and eventually to methanol via this multi-step industrial process that involves high operating temperatures and high pressures. Of course, this is a fairly expensive process, and we'd like to be able to do this conversion in a direct and selective fashion, going straight from methane to methanol at moderate reaction conditions in the presence of a catalyst and some oxidant. One of the common active site motifs that has been invoked for this reaction are terminal Metal-Oxo species. For instance, you might start with a coordinatively unsaturated metal center, and you'll introduce some oxidant like N2O or H2O2 or O2, and form this terminal Metal-Oxo species that I'm showing here. You can imagine this being as part of a MOF, where you have these coordinatively unsaturated metal centers, and you can oxidize those and then flow methane through the pores of the MOF, and hopefully you can convert that methane to something more valuable. And what we want to ask ourselves is what makes a promising catalyst for this reaction? How can we design a MOF with the desired properties to carry out this very challenging process? To demonstrate some of the trends I want to discuss with you today, I'll be specifically focusing on a given MOF family, which I'll call the BBTA family for short. This MOF family is synthesized by taking a metal salt and a so-called BBTA linker, which is a triazolate-containing linker that you see here. Together, this forms a honeycomb-like structure with a pore diameter of about 13 angstroms, depending on the metal and ligand. If we take a zoomed-in look here into the screen, what you'll see is that you have a chain of metals, shown in orange, that are connected to one another to form this so-called infinite rod-like topology. And those metals are, again, connected via those organic linkers. In addition, those metal centers are bridged by this species shown in green, which is a monovalent bridging anion. This depends strongly on the synthesis conditions you use to make them off, depends on that metal salt, and in this case, it could be something like chloride or fluoride or bromide or OH. A wide assortment of different monovalent anions have been used to make this MOF to date. What is really interesting about this material is you can tune not just the metal center or functionalize the linker, but you can also tune that first coordination sphere by modifying out those different bridging ligands. And this is what I want to discuss today, is what is the effect on that first coordination sphere on the electronic properties of the metal center, and how does that influence the catalytic reactivity for converting methane to more valuable products? So what we want to ask ourselves now is what do we need to calculate to really understand what makes a promising catalyst for this class of reactions? In particular, we of course need to be able to form the proposed active site. And as I mentioned before, one of the commonly invoked active site motifs for catalytic conversion of methane is a terminal Metal-Oxo species. To start, the guest Freemov has a square pyramidal coordination geometry around the metal center, and so an oxidant can bind there and form that Metal-Oxo species. And what we'd like to understand is that process thermodynamically favored or unfavored? In this case, we can calculate that Metal-Oxo formation enthalpy as simply the product minus the reactants. Of course, forming the proposed active site motif is just one part of the bigger picture. We also need to make sure that, if formed, that Metal-Oxo species can break the strong CH bond of methane. So the other parameter of interest that we'll be calculating is the apparent activation enthalpy for breaking that CH bond of methane. In this case, what we can imagine is we have our active site once formed, and we have methane fairly far away. It can then absorb nearby that Metal-Oxo active site species, and then there's some intrinsic barrier for breaking the CH bond. In this case, I'm going to specifically be comparing the apparent activation enthalpies between catalytic candidates, because in prior work, we've shown that the absorption energy of methane around these Metal-Oxo active sites is essentially a constant value between different MOF candidates, particularly when the pore size of the MOF doesn't change very much, like in the BBTA family of MOFs. So now that we have an understanding about what the important parameters of interest are, let me jump into some of the results. What I've done is I've used density functional theory calculations to explore the catalytic reactivity of this family of MOFs with different metal centers and different bridging ligands, depicted as X here. What I'm showing on the X-axis are those different metals, and each bar represents a different bridging ligand. On the Y-axis is the Metal-Oxo formation enthalpy. As a reminder, we want this value to be exothermic, or at least not so endothermic that the process simply can't occur at all. With this in mind, there are three key takeaways that I'd like to bring to your attention. The first is that there are clear periodic trends as you go from the early to late transition metal cations. You can see that the early transition metals tend to have more exothermic metal oxoformation energies. We tend to say that's more redox active. Those metal centers are more readily oxidized, going from that formerly 2 plus state to start out to the 4 plus state when it forms that metal oxo motif, and that's a fairly favored process. But as you go to the late transition metal cations, that metal oxo formation enthalpy gets more and more endothermic, indicating that metal oxo bond is getting significantly weaker until eventually it probably just can't form at all. This is very much in line with the idea of a metal-oxo wall in inorganic chemistry, which states exactly the same thing, that as you go from early to late transition metals, it becomes harder to form that proposed metal-oxo species until eventually it can't be formed at all, and it becomes very difficult to isolate. The second takeaway is that if we look at a given metal and we compare the different energies associated with the bridging ligands, what we find is that the metal oxoformation enthalpies tend to be more exothermic for the bars in blue, which are the OH, SH, and SEH bridging ligands, as opposed to the halogen ligands shown in purple. And this tends to hold for all of the metals that I've considered here. So this is one useful design rule. If you want to design MOFs with more redox active metal centers, perhaps what you'd like to do is use the OH, SH, or SEH bridging ligands in general. And as for this last point, what I want to do is focus on a given metal, let's say vanadium, and let's take a look at a given class of ligands like the halogens. What we see is that the more basic bridging ligand tends to yield a more redox active metal center. For instance, the vanadium MOF with fluoride bridging ligands has a more exothermic value for the metal oxoformation enthalpy than the bromide and chloride bridging ligands. Again, the same trend holds for chromium and manganese, as well as iron. But there's a switch. At cobalt, nickel, and copper, what we see is that the more basic bridging ligands no longer tend to yield the more redox active metal centers. It's actually the opposite trend. And while I don't have time to go into all the details for why this might be, what I'll just say is that it's a complex interplay between the electron donating character of the ligands, which donates electron density to the metal center when it gets oxidized, and the electronegativity of those bridging ligands, which of course does the opposite and withdraws electron density. So now with a better understanding about how we can potentially form that metal oxo active site motif, what we should now do is turn our attention to how reactive are those hypothesized metal oxo species for the catalytic CH bond activation process we're interested in. So now that's exactly what I'm showing. On the y-axis, we have that apparent barrier that I mentioned before for breaking that CH bond of methane. And on the x-axis, we again have the different catalysts of interest with different metals and different bridging ligands. What we see here is that for the most part, most of the catalysts have fairly low apparent barriers. And while there's some trends, you could see the vanadium containing MOFs tend to have the largest barriers, and the later transition metal cations have the lowest barriers. By and large, the trends with respect to ligands is a little bit more complicated than it was for forming that metal oxo species in the first place. Now, where things get really interesting is when we take a look at the electronic structure of the metal centers when we consider different bridging ligands. What we need to do now is first understand what the electronic structure could potentially look like. In this case, we could have something that's more formally a metal oxo species, like I've been alluding to before. This would be you start with a metal that's in the 2 plus state of the MOF, and it gets oxidized to the 4 plus state, and the oxygen ligand is then in the 2 minus state, and is a fairly high bond order. But there can also be a metal oxyl radical instead, where it gets partially oxidized, that metal center, and the oxygen has a formal charge of -1, and there's a radical center located on the oxygen species. And then there's the extreme limit of no bonding at all, but that's very unlikely and is just an extreme case. What I want to emphasize is that most likely, depending on the ligand and the metal you choose, you're going to exist somewhere along this spectrum, and that potentially will influence all the catalytic properties. Now, one property of interest that I wanted to probe using the density functional theory calculations is this idea of spin density, which is a measure of the degree of radical-like character centered on a given atom. So, for instance, if we take a look at the iron 3 oxyl species and an iron 4 oxo species, the spin density on the oxygen atom at the oxyl radical is formally a spin density of 1. There's one unpaired electron localized on that atom. Whereas for an iron 4 oxo species, formally there would be a spin density of 0 localized on that oxygen atom. There's no radical center there. I should mention that we can compute the spin density in other atoms in the MOF as well, such as on the metal centers, which will tell us how many unpaired electrons there are localized on that atom. So in this toy example, if we take a look at the iron 3 oxyl radical, where I've arbitrarily drawn the iron 3 species as being in the high spin state, in this case, the iron would have a spin density of about 5, and in the iron 4 oxo species, that spin density in the iron center would be about 4. The reason we need to start thinking about things like spin density, the electronic structure, and just spin in general is that there's this idea of two-state reactivity in the literature, or even multi-state reactivity. This general concept states that for a given reactant, transition state, and product, there are potentially multiple spin states a given transition metal complex or MOF could exist in. So for instance, in this example, the reactant is most stable in the singlet spin surface with no unpaired electrons, and the triplet spin surface is higher in energy. The same is true for the product, but at the transition state, it's actually not the case. At the transition state, there's a lower energy spin state that's in the triplet state as opposed to the singlet state, which lowers the effective barrier. And in this case, there's a spin crossover behavior en route to the transition state and then back to the product. This spin transition could potentially occur anywhere or nowhere in the mechanism, and this is an important factor we need to consider because this can potentially influence the reactivity. So before I discuss what the big takeaway is here, I need to introduce one bit of sign convention. Specifically, before I was just talking about an absolute value of the spin density, irregardless of whether it's spin up or spin down. In this case, by convention, I'm just going to define all the spin density on the metal center as being arbitrarily spin up. This means that if there's ferromagnetic alignment between the unpaired electron density on the metal and any unpaired electrons on the oxygen atom, then that's going to be a spin density that's positive on the oxygen ligand. Whereas if there's antiferromagnetic alignment between the spin density on the metal center and the oxygen ligand, I'm going to use a sign convention of negative for the spin density localized on that oxygen center. Again, a negative value will just indicate antiferromagnetic behavior and a positive value ferromagnetic behavior between the metal center and the oxygen species. So if we look at the right-hand side, what I'm showing is the spin density on the oxygen atom for that Metal-Oxo species for the different metals I've considered, as well as all the different bridging ligands I've considered, where I've just jittered each one of those on the x-axis just to make it visually easy to tell apart. Now, if we take a look at the magnitude of the spin density on the oxygen atom, what we see as we go from early to late transition metal cations, that spin density on the oxygen atom gets greater and greater, and that's indicative of the idea I was talking about before, where that metal-oxo species is going to have a weaker and weaker bond order, going from a metal-oxo to a metal-oxyl to a formerly very little bonding at all. But we can also take a look at the sign on that spin density. Once again, negative means anti-parallel alignment, and positive means parallel alignment. And we'll talk about why that is important in just one moment. On the right-hand side, I'm now showing the spin density of the oxygen atom at the transition state for CH bond activation. And again, what we see is that there are some periodic trends, but what I really want to draw your attention to are the MOFs that are shown in these purple boxes. What we see is that for the manganese and iron containing frameworks, the spin density at that initial metal-oxo species is aligned in a parallel fashion between the metal center and the oxygen. However, at the transition state, there's an anti-parallel alignment, such that there's a switch, again, between the sign of the spin density on the oxygen atom, going from aligned to anti-aligned. This only occurs for the manganese and iron containing frameworks. All the other ones, that spin alignment stays exactly the same. And what I'm going to show you on the next slide is that this makes all of the difference. Now let's take a look at the manganese containing frameworks for a moment. I'm just going to highlight the manganese fluoride BBTA framework just as an example, but all the results I'm going to show here are independent of the choice of ligand. On the left-hand side of this figure is the metal-oxo species before any reaction has taken place, and of course that species can exist in one of several possible spin states. In this case, the lowest energy spin state is the spin 3/2 state, with ferromagnetic alignment between the spin density on the metal center and the oxygen ligand. On the right-hand side of this figure is the transition state for cleaving that CH bond. Again, that species can exist in one of several possible spin states. What we see is if we stayed on the spin surface shown in red, which was the ground state spin surface for that initial state, the spin 3/2 ferromagnetic alignment state, what we see is that the barrier is about 120 or so kilojoules per mole. If instead we only consider the ground state species for the initial state and the transition state, we see that there's a spin crossover behavior such that it goes from being ferromagnetically aligned between the metal center and the oxygen atom to anti-ferromagnetic alignment of that spin density between the metal and the oxygen atom, which greatly reduces the barrier by upwards of 90 kilojoules per mole. So a huge difference. And so this is something that I want to emphasize that we need to consider in our density functional theory calculations. You actually do need to consider all these different arrangements, and it's easy to overlook. But also, it's this phenomena that really drives down that barrier and makes it even more reactive. I should mention that the same results hold for the iron-containing frameworks as they did for the manganese ones. Again, we start with an initial state which can exist in one of several possible spin states. In this case, the ground state spin state is the S equals 2 state, again with ferromagnetic alignment between the spin density on the metal and the oxygen. And for that transition state, if we instead have a spin crossover behavior to the same spin multiplicity, still the S equals 2 state, but now with an anti-parallel alignment between the spin density on the metal and the oxygen atom, we see that again greatly reduces the barrier. And so what I want to just reemphasize is that the spin multiplicity is not changing here throughout the mechanism. What is changing is the alignment of those electrons. So the net number of unpaired electrons stays the same, but the alignment differs, and that has a huge effect on the kinetics. One way to rationalize this phenomena is that pathways that increase the spin density on the metal center tend to yield the lower barriers. So I'm not showing the other pathways here, but this particular set of ground state pathways with the manganese and iron containing frameworks increases the spin density on the metal center, which you can see here. This tends to stabilize the transition state, like an extension of Hund's rule, but for transition metal complexes, where the structures are more stable with more unpaired electron density, as opposed to being all paired up. This is a very subtle phenomenon, but it's clearly one that can make a huge difference on the overall performance of a given catalytic candidate, and it might be something that we would like to engineer and insert MOFs in the future. So with all this being said, I have several recommendations for future work. If you're looking to make more redox active metal centers, ones that could potentially more readily form those Metal-Oxo active site species, I'd recommend using the OH containing ligands in general, and for at least the early to mid transition metal cations, using the more basic bridging ligands. I should also mention that the manganese and iron frameworks we studied here exhibit this unique spin transition behavior that greatly reduces the barrier for CH bond activation. In terms of future directions, we could try to better understand how to tune that anti-ferromagnetically enhanced reactivity between the metal center and the oxygen ligand via modifications to the coordination environment of the MOF. And then finally, we can use these principles to design top-performing MOF catalysts for this very challenging class of oxidation reactions. So with that, I want to say a big thank you to my advisors, Professor Randy Snurr and Professor Justin Notestein, as well as the funding and computing resources that made this work possible. If you'd like to read more about this work, it was recently published in Angewandte Chemie, and you could check out the article here on the iPoster. If you have any questions at all, please don't hesitate to reach out to me via my email. I'm happy to chat about this further and answer any questions you may have. Thank you, and I hope you enjoyed my talk.